Greetings, everyone, and welcome to the Pan Future Podcast. I'm your host, Sean. Today is Saturday, August 12th, 2017. I do have a fairly long regular segment this week continuing our discussion of nanotechnology, so I'm going to forego the regular news this week, but I will open with this. There's been a photo going around some of the science pages lately, and it's worth talking about and mentioning here. It's a page of Carl Sagan's 1995 book, The Demon Haunted World, and this book is one of the essential books of science and skepticism. If you haven't read it, you really should. But the section of the book here, there's a page and there's a part of it highlighted, and I'm just going to go ahead and read that part here. He's talking about the reasons you should teach science, and the reasons science is the best way to navigate the world, and sort of lamenting that it's not taught as much as it should be. And he writes, I have a foreboding of an America in my children's or grandchildren's time when the United States is a service and information economy, when nearly all key manufacturing industries have slipped away to other countries, when awesome technological powers are in the hands of a very few, and no one representing the public interest can even grasp the issues. When the people have lost the ability to set their own agendas or knowledgeably question those in authority, when, clutching our crystals and nervously consulting our horoscopes, our critical faculties in decline, unable to distinguish between what feels good and what's true, we slide, almost without noticing, back into superstition and darkness. The dumbing down of America is most evident in the slow decay of substantive content in the enormously influential media. The 30-second sound bites, now down to 10 seconds or less, lowest common denominator programming, credulous presentations on pseudoscience and superstition, but especially a kind of celebration of ignorance. There you have it, from over 20 years ago. Carl Sagan essentially predicting exactly the way things are right now. People don't trust science. They think that whatever you feel is the right thing to do. Facts don't matter. It's sad to me that this was A, predictable, and B, I don't know how to get around this. I guess that's why I do this show. In my small part, maybe I'm reaching a few people. Maybe I am expanding minds. Maybe I am helping people think critically about the information that they are receiving from everywhere. And that not everybody who says something knows what they're talking about. There are opinions, and there are statements of fact. And we need to be able to understand the difference between the two. And just on a topic of civilization in general, because this comes up over and over and over again, people don't understand what freedom of speech is. It's something that will be in the news these next few days here in the United States. Freedom of speech means that, yes, you can pretty much say just about whatever you want in public. It means that the government cannot arrest you for what you say, as long as you're not actually making some sort of threat. It does not mean that everybody has to listen to you or believe you. If you want to stand in the public square and declare chocolate an octave of the sun and tell people that silver cannot be molded during the eclipse, I'm looking at you, David Avocado Wolf. The rest of us are you can say that. You have the absolute right to say that. And the rest of us have the right to stand up and say you are a moron. That doesn't even make sense. It's word salad made out of lettuce and tomatoes and raw hamburger. Those words in the English language don't go together that way. It doesn't. See, I get really wound up about this stuff, so facts matter. I'm going to harp on that over and over again. There are actual experts, people who know what they're talking about, and you need to learn the difference between someone with a background who understands science and someone who doesn't and is just making up crap to scare you and then sell you the thing that is supposed to cure you. All right. That's my rant. I guess I didn't really mean to rant there. Let's get on with the show, shall we? Take a breath. Think about the future. Dream a little bit. Be hopeful. Sounds good to me. All right, on the main segment this week, we continue our introduction to nanotechnology. I want to get into a few examples of how people actually work at this scale and spend a little time speculating about the far future. As many technologies I have discussed last episode become more widely available and more widely used, we will shape the world around us like never before. For further reading on nanotechnology, in addition to the show notes, I actually highly recommend Nanotechnology for Dummies. The Dummies series of books are actually quite good at being very clear and understandable and aren't really insulting, as the title might imply, and don't really dumb things down too far. I really think Carl Sagan would actually like the Dummies books on science. There's all kinds of science Dummies books, nanotechnology, neuroscience, all kinds of things. Anyway, without the nanotech book, I could not have researched this episode, and it's worth a read for an even more extensive look at nanotechnology than I have time here for. One of the most basic questions I had when starting research for the show is just how does one work at such small scales? How do you build something one atom at a time? Nanoscale work can be done two ways, bottom up and top down. In the first, you would build something one atom or one molecule at a time in an additive process. In the second, he would carve away a surface, a subtractive process. This top-down method is currently in use for making computer chips and other things, while the bottom-up approach is mostly in experimental stages still. Self-assembly is a third method for building at the nanoscale. In placing atoms or particles in certain conditions like various temperatures and electrical charges, behavior of self-assembly can be manipulated, and the atoms will arrange themselves in certain ways. Some consider this another bottom-up approach. At the nanoscale, properties such as chemical reactions, reactions to light, and melting points are different than they are at macro scales. A major invention that set the industry on its way was the scanning tunneling microscope, invented in 1981 by IBM researchers Gerd Binnig and Heinrich Rohr. Hopefully in the near future I'll find a guest to come on the show and talk nanotech because my understanding is reaching its limits. In my attempts to understand the scanning tunneling microscope, I checked the Wikipedia page and it was over my head. I found that Wikipedia actually has a project of simple English explanations, sort of like the Dummies book. So this is from the simple wiki on the scanning tunneling microscope. Scanning tunneling microscopy is a way to view atoms. It was developed in 1981, invented by Gerhard Binnig and Heinrich Rohr at IBM Zurich. They won the Nobel Prize in Physics for inventing it in 1986. For STM, good resolution is 0.1 nanometers lateral resolution. That's how accurately you can see features on the surface. And 0.01 nanometer depth resolution, that how accurately it can see the height of bumps on a surface. The STM can be used not only in a vacuum, but also in air and various other liquids or gases, and at most common temperatures. The STM is based on quantum tunneling. When a metal tip is brought very near to a metal or semiconducting surface, a voltage between the two can allow electrons to flow through the vacuum between them. Changes in current as the probe goes over the surface is what makes the picture. STM can be a hard thing to do as it needs a very clean surface and sharp tips. First, the tip is brought very close to the thing being looked at, about 4 to 7 angstroms. An angstrom is 100 millionth of a centimeter. Then the tip is moved very carefully across the thing being tested. This change in current when it is moved can be measured, a constant height mode. The height of the tip where it always has the same current can be measured too, as in constant current mode. Using a constant height mode is faster, and the parts of a scanning tunneling microscope are the scanning tip, something that moves the tip, something that stops it from vibrating, and a computer. All right, so there you have the absolute simplified explanation of a scanning tunneling microscope. That is as simple as I think it can get and still actually make some sense as to understanding what it's doing when people are working with it. To me, it's more of a vinyl record stylus than a microscope, but at any rate, it was the invention of this device that opened the door to working on the nanoscale. The scanning electron microscope also has a role in nanotechnology, though its resolution is not as small as the scanning tunneling microscope. Not long after imaging at the nanoscale was discovered, it was also discovered that the same techniques could be used to move individual atoms. In 1989, Don Eigler, also of IBM, arranged 35 atoms on a nickel surface to spell IBM. Small beginnings, but I think it's interesting to see how new all of this technology is. Many of the topics I've covered have roots going way back, sometimes even centuries. Nanotechnology is even newer than artificial intelligence. Manipulation of atoms does require very clean environments, super cool temperatures, and a vacuum. Perhaps near future development would mean manipulation at room temperatures. Also, around 1985, Harry Kroto, Richard Smalley, and Robert Curl all did work which led to the discovery of buckyballs, a carbon sphere-like structure that is very stable. Then, in 1991, carbon nanotubes were discovered, or rather proved, by Sumino Iijima. These carbon structures, due to their stability, conductivity, and other properties, are major areas of nanoscale research. Graphene, carbon sheet only one atom thick, is another carbon-based structure with many potential applications. In some ways, working with atoms isn't all that different than working at the macro scale. For example, to coat something with gold using a scanning electron microscope, and this description from the Dummies book, put your sample in a small sputtering chamber that contains a gold target. Argon gas flows into the chamber and is ionized by an electric field. The argon ions, in a process called sputtering, hence the name of the chamber, strike the gold target and knock off some gold atoms into the chamber, and those atoms then coat your sample. So that process is not unlike how things would be done to spray paint or to atomize something at a larger scale. Using a scanning tunneling microscope, it is possible to move one atom at a time using the van der Waals force. Named after physicist Johannes van der Waals, it is a weaker force that acts on atoms and molecules at very small scales. Using the STM and 2 layers of materials, I think I can best describe the process as being similar to picking up something with a magnet through a piece of wood. The magnet and the other magnet or whatever you're picking up don't actually touch each other, but are still held together. Anyway, the point is, the scanning tunneling microscope does not actually touch the atom that you're moving, but allows for 2 atoms to latch onto each other. Then you can move the atom, raise the tip of the STM, and deposit the atom where you want it. I think this sounds like a pretty tedious process, and large-scale manufacturing is probably down the road a little ways. Another possible method of manufacture is by using nanorobots. The tiny robots could be programmed to build just about anything. There is research being done in both biologically based robots and mechanical and synthetic ones. If it's hard to imagine tiny biological robots, just remember that the behavior of DNA and proteins in our bodies is basically that of tiny machines. Using these traits and the traits of things like viruses, it's not really a huge stretch to imagine biobots doing work for us. Mikhail Rocco of the Nanotechnology Initiative has suggested that nanotechnology development will occur in 4 steps. Step 1, passive nanostructures, which he describes as materials designed to perform one task. Step 2, active nanostructures for multitasking. These would include devices to deliver drugs in a targeted way, for example. Step 3, nanosystems that might involve thousands of components interacting with each other. And step 4, integrated nanosystems, including systems within systems that could accomplish far more than we can today, such as sophisticated molecular manufacturing of genes inside the DNA of targeted cells, or the nanosurgery for healing wounds on the cellular level. We are currently able to work with materials in the first 2 stages, while the latter 2 are more in the hypothetical and research stages. Nanotechnology is a staple of science fiction. How much of that might come true? We use nanotech to deliver medicine. Will future delivery be even more precise with medicine delivered by intelligent nanobots? Perhaps swarms of nanobots will be used to shape vehicles or spacesuits, then be able to change shape as needed. Nanobots might not even be necessary. As we get better at manipulating materials at the nanoscale, we could have liquid-like materials that reshape as needed. Think Terminator 2, but less threatening. Or maybe the ship from the movie Flight of the Navigator. Or Nemesis from Dan Simmons' Hyperion books, although her abilities are not stated as being nanotech, but one could guess that's how it would be done. Nanomaterials are already used to improve strength and durability, but in the future they may be the major component that leads to breakthroughs in constructing a space elevator, or could offer previously unimagined ways of constructing spaceships or shelters for astronauts. Might nanobots be incorporated into 3D printing, allowing the use of any material, Mars rocks, for example, to be turned into just about anything else. Although some feel a threat from nanotech, not entirely without merit. I think it is possible that we are in the early stages of a new industrial revolution. All right, that's the show for this week. Thank you, as always, for joining me. I really appreciate everyone who tunes in. I guess you don't really tune in, downloads the show. If you do want to help out the show, there's a donate link on the website, panfuture.org. You can also send me email from there, find the Twitter feed or the Facebook stuff. Write a review on iTunes. That is always very helpful as well. Also, if you're interested, on the About page on the panfuture.org site, you'll find links to my music. All of my music is downloadable for free, but if you feel like tossing a donation in there for the music, that is always appreciated as well. I'm also working on a little something to support the show and to support some of my other work, so I expect to be making an announcement about that soon, so stay tuned. And one last time, thank you. I will talk to you again in the future.